Imagine standing on the surface of Mars. Rust-colored dust stretches to the horizon, and a compass would be useless here, because unlike Earth, this planet has no global magnetic field to point it toward. But tens of thousands of kilometers above your head, something violent and completely invisible is happening. Magnetic field lines are snapping apart and reconnecting into new shapes, hurling charged particles across space at hundreds of kilometers a second. That snapping process has a name. Physicists call it magnetic reconnection, and it might be one of the most important things happening in space that almost nobody outside a physics department has ever heard of. Here is a way to picture it. Take two ropes, each one a bundle of magnetic field lines, and push them together from opposite directions. Under the right conditions, instead of just pressing against each other, they snap and reconnect, like a rubber band twisted too far suddenly springing into a new shape. All the energy stored in that tension does not just disappear. It converts almost instantly into heat and raw kinetic energy, blasting the surrounding particles outward like a slingshot. You have almost certainly seen the results of this process, even if you never knew what caused them. Every time the northern or southern lights ripple across a polar sky in green and purple curtains, magnetic reconnection is part of the machinery behind that light show. Earth's magnetic field gets stretched and loaded with energy by the solar wind, and when it finally snaps back through reconnection, it dumps charged particles into the upper atmosphere, where they collide with oxygen and nitrogen and glow. The same basic process, scaled up enormously, powers solar flares and coronal mass ejections, the giant eruptions that occasionally send a wave of charged particles racing toward Earth, the kind that can spark auroras far outside the usual polar range and rattle satellites and power grids. So here is a question worth sitting with for a second. If this invisible snapping process is powerful enough to light up the sky and threaten power grids on Earth, why did it take until the 20th century for anyone to even propose that it was real? For decades, scientists could not explain how the sun's atmosphere released energy so explosively, or how Earth's magnetic environment seemed to breathe in and out with the solar wind. The picture came together in pieces, and in 1964, a physicist named Harry Petchek worked out the geometry that let reconnection happen fast enough to match what observers were actually seeing. Petchek's model described a very specific shape. Two boundaries bent outward like the wake behind a boat, with a stream of fast, heated plasma shooting out between them. Decades later, that exact shape is still what scientists look for as the fingerprint of reconnection in spacecraft data. But here is the thing about reconnection that makes it so interesting to study. It should not just be a trick that Earth and the Sun happen to share. If the physics is universal, it should be happening constantly, everywhere in the solar system where magnetized plasma flows and collides. The solar wind itself, the constant stream of charged particles blasting outward from the Sun in every direction, is full of opportunities for that. As it rushes outward, it gets threaded with thin boundaries called current sheets, places where the magnetic field on one side points in a noticeably different direction than the field on the other. Spacecraft near Earth have been catching reconnection happening inside these current sheets for 2 decades now. More recently, NASA Parker Solar Probe has even spotted it remarkably close to the Sun itself, confirming the same physics operates all the way from the solar corona out into deep space, which raises an obvious follow-up question. If reconnection is common near Earth and common near the Sun, what about everywhere in between? What about at other planets? That question gets especially interesting at Mars, because Mars is not like Earth in one crucial way. Earth generates its own global magnetic field deep in its molten core, strong enough to wrap the entire planet in an invisible shield called a magnetosphere, deflecting most of the solar wind before it ever reaches the upper atmosphere. Mars used to have something similar, billions of years ago. Ancient magnetized rock on the Martian surface is essentially fossil evidence of a global magnetic field that shut off long ago, likely as the planet's core cooled. Without that shield, Mars has spent roughly the last 4 billion years directly exposed to whatever the solar wind throws at it. Many scientists think that exposure is a major reason Mars went from a world with a thicker atmosphere and evidence of ancient rivers and lakes to the thin, cold, dusty planet we see today. Over enormous stretches of time, the solar wind may have slowly stripped away the atmosphere Mars once had. So here is a question worth sitting with for a second. If a planet does not have a global magnetic field of its own, is it simply defenseless against everything the Sun throws at it? Or does something else step in? Mars is not entirely unprotected. As the solar wind slams into the top of its atmosphere, it induces a weaker, messier magnetic bubble called an induced magnetosphere, generated on the fly by that collision rather than by anything happening deep inside the planet. That makes Mars a genuinely strange laboratory, sitting somewhere between a fully shielded world like Earth and a completely bare object like the Moon, wrapped in a magnetic environment improvised, moment to moment, out of the collision between the solar wind and a thin atmosphere. To study that environment up close, NASA needed a spacecraft built specifically for the job. That spacecraft is called MAVEN, short for Mars Atmosphere and Volatile Evolution. It launched in November of 2013, settled into orbit around Mars in September of 2014, and has been circling the planet ever since, carrying instruments built to measure the magnetic field, ions and electrons swirling around Mars in extraordinary detail. MAVEN mission is essentially built around one big question. How is Mars losing its atmosphere to space today? And can watching that process in real time help explain how the planet transformed over billions of years? MAVEN was not the only spacecraft in the neighborhood, either. In 2021, China's Tianwen-1 mission arrived at Mars, becoming the country's first fully successful interplanetary mission, carrying an orbiter, a lander, and a small rover into a system that suddenly had two independent sets of eyes watching the same space weather from different angles. Researchers already knew that current sheets, those thin boundaries in the solar wind, show up regularly near Mars. Earlier studies had cataloged plenty of them. But there was a catch. Every previously observed boundary near Mars looked static. The magnetic field flipped across them, sure, but nothing seemed to be actively snapping and reconnecting inside them. No outward jets of particles. No sign of the pear shape scientists knew to look for. So even though reconnection had been confirmed near Earth, confirmed near the Sun, and was assumed on theoretical grounds to be happening basically everywhere magnetized plasma exists, nobody had ever actually caught it in the act at Mars. That gap sat there, unresolved, until a team of researchers from Boston University, Princeton, the University of Iowa, UC Berkeley, and several other institutions decided to comb back through years of MAVEN archive data looking specifically for it. So when the team pulled apart years of measurements from a spacecraft that has been quietly circling Mars since 2014, what did they actually catch happening for the very first time? They found two clean, unmistakable cases. One from June of 2025, and buried deeper in the archive, an earlier one from January of 2015, just months after MAVEN had arrived. In both events, MAVEN was sitting well upstream of Mars, bathed in a cold, undisturbed solar wind, when its instruments picked up a current sheet sweeping past. The magnetic field rotated sharply across a narrow region, in one case by more than 135 degrees, in the other by more than 156 degrees. That rotation alone is not proof of reconnection. Plenty of current sheets simply sit there, flipping the field without anything more dramatic happening. What convinced the researchers was what came with the rotation. In both events, the magnetic field split into two distinct steps, a clear signature of a boundary that had bifurcated, exactly the shape Harry Petchek described back in 1964. And riding along with that split field, ions were streaming outward at speeds closely matching the MAVEN speed, the specific velocity at which disturbances travel through a magnetized plasma, the telltale signature of a reconnection jet rather than an ordinary current sheet. To check the math, the researchers ran what is called a Weyland test, comparing how closely the plasma's velocity matched the theoretical MAVEN velocity. A near-perfect match is strong evidence the outflow really is a reconnection jet. The first event scored a correlation of 0, 82. The second scored 0, 77. Both comfortably inside the range that says yes, this is really reconnection. Ion temperatures ticked upward inside both exhaust regions too, exactly the gentle heating you would expect when magnetic energy converts into particle motion instead of just vanishing. Put together, the bifurcated field, the fast aligned outflow and the heating gave the team what they needed. Direct, physical proof that magnetic reconnection is happening in the solar wind right next to Mars. Not just theoretically possible, but caught in the act. But it was the scale of what they found that genuinely surprised them. Current sheets near Mars are usually thin, typically only 1 to 2 Mars radii across, somewhere around 3,400 to 6,800 kilometers. The two reconnection exhausts measured in this study were enormous by comparison, stretching 17, 2 and 6 Mars radii respectively. The larger one alone spanned close to 60,000 kilometers, roughly a seventh of the entire distance between the Earth and the Moon. A boundary that size does not just flip a magnetic field locally. It suggests reconnection can dramatically stretch and reshape the structure of the solar wind, as the exhaust plasma keeps flowing outward from wherever it first ignited. For the larger of the two events, the team got a genuinely lucky break. China's Tianwen-1 orbiter happened to be flying through the same region of space at the exact same time, roughly 4-5 Mars radii away from MAVEN. Tianwen-1 recorded its own independent measurement of the magnetic field, and it showed the same signature rotation MAVEN had just detected. Two spacecraft, built by two completely different national space programs, sampling the same invisible event from two different points in space at the same moment. That is about as strong a confirmation as this kind of measurement can get. The researchers are careful, though, not to overstate what two events can prove. This is a demonstration that reconnection happens at Mars and behaves physically like the reconnection already documented near Earth and the Sun, not a full statistical map of exactly how often it occurs or precisely how much it matters, day to day, for the planet as a whole. The measured effects on the surrounding solar wind, in these two cases at least, were fairly modest. Dynamic pressure inside the exhaust regions rose by about 5% in the first event and about 4% in the second, compared to the plasma just outside. Not the kind of dramatic swing that would visibly reshape the Martian atmosphere in one single event. But modest effects add up differently on a planet with no global magnetic shield of its own. Mars lost most of its atmosphere over roughly 4 billion years, one slow interaction at a time, and confirming that reconnection is an active, ongoing process in that exposed environment fills in a piece researchers did not have a direct measurement for before. It matters for reconstructing how the planet's climate collapsed over deep time, and it matters for something more immediate too. Every future crewed mission to Mars will operate inside this exact unshielded environment, with no global magnetosphere standing between astronauts and whatever the sun's outbursts send their way. Understanding exactly how energy and particles move through that space, reconnection included, is not an abstract physics curiosity. It is part of the groundwork for keeping people safe on a planet that lost the magnetic shield we take for granted here at home. So the next time you look up at a night sky untouched by aurora, remember why. The same invisible process that occasionally lights up our own poles has now been caught snapping and reconnecting quietly around Mars too, a planet that gave up its own version of that shield a very long time ago, and is still, right now, feeling every consequence of that loss.